Okay guys, for the second part of this video, we will going to just discuss about the other topic of this section of the chapter number 3, including the residual diagnosis, the evaluating of forecasting accuracy. That's very important. Prediction interval, and finally introduction about the forecast packet in R. So this could be a very a little bit long video, and you will have to pay more attention in it, please. So first we talk about the residual diagnosis. When we already generate for the forecasting model, we can apply them, right? And based on all the data that we already got it, so we can use it to just do the forecasting, and we create for the like fitness value. That will be actually the data that's be generated by the forecasting model. But however, all the data before we can also use for the data that we use to generate for the model to create for the new data, and they can overlap into the previous historical data. The fitness value, they will be the value that calculated by the model, and they are not necessarily equal to the real value, or what people call the observed values. And that's the reason why when we generate for the fitted value, there was some residual or the difference between the real observed values and the fitted values, and this is what we call the residual in forecasting. And some assumption about the forecasting, we can say about the residual must be uncorrelated, and they should have the mean 0. However, the other useful properties that we going to use for later with the prediction interval in the section 3.5, that the residual also have to have the constant variance, and they should be normally distributed. To do this, we're going to check for the residual of them to see like how they fluctuate with the time series when we generate for the residual, how they are distributed through the histogram, and how they are autocorrelated with the autocorrelation function of the residual chart. So based on this all, we going to generate it into some assessment and diagnosis of the residual. Also, we provide some box cuts. The Legend box. That should be a kind of like hypothesis testing methods to just generate and to see like if the residual really so white noise or not. And we're going to check it right now in the practice on our studio. So first of all, in this section, I will use the Google 200, okay, for just practices. So if you have a practices in the section 3.1, I guess you'll be fine with that. If not, so this is the daily closing stock price of the Google, and they have like 1,000 consecutive trading day between February 25 to 2013 into the February 13 of the 2017, about like almost 3 years, 4 years. And with the adjusted aspect, but we basically just think about like this daily price, okay, daily price. And we go into to just exploit a little bit, okay, and STR to see the structure of the Google 200. And we see like over here, this is time series with the 200 observation, okay, the 200 observation contain the first 200, okay. So they just include the first 200 observation of this data, and we're gonna to check it like about we gonna just I want to plot the Google 200 time series, okay. Let's go and check it by the auto plot or whatever you want, okay. Google 200 okay, and then I apply for the pi operation, and I want to check it for the auto plot, okay. Alright, this will look like this. Of course, I will not just stop it there. I want to just make it add another layer to make it everything become like clearer. So I put it like day for the X level, for the Y level. In another ways, I would say that should be closing price in USD. Okay. Alright, and I want to do it also for the CG title. So I really want to see like how everything will be put into the right order. The daily ending on the 6th December. Okay, 6th 2013. Okay. So let's just go and check this one first. So this fluctuate, right, and then they have some kind of trend, but not so clear. They're not like continuous trend, but they for the first like 60 day of the or 50 day of the data, 60 day. So they have a kind of increasing. But however, from let's say the day 60 into 100, I guess 70 or like 60, they fluctuates around 425 to 450, and later right after the day of the 160 or 170 they have a like big jump. They reach into the new peak of the 500 and then they going up. Okay, so this is all the thing happened in the last 200 day of the data. And now let's just go and check for the fit values. Okay, check the fit between the result, okay, the fitted result and the real observed data. Okay, and like how I'm gonna do it, I'm still one more time use for the function, and this one I'm gonna just use it for the very easy understand the native function. So I would just do the forecasting based on the native method. Okay, the native method. Alright. Okay, this is the forecasting for the next 10 days. So basically, if you don't really gonna to fit it, they will just forecast it for the next 10 days. Okay. Alright, and now let's go on to do it, and use the fitted function. Okay, the fitted function will just generate for all the data from the day 1 into day 200 based on the native method. Okay, and we use the value of the first day to forecast for the second day to forecast for the third day, and so on. And that's what we're gonna do. So they pick all the value, right? They no longer previous data, but they check it and they just do the name method to generate for the another 200 day, and this will be what we call the fitted values. And I will gonna assign it into the object called fit. Okay, this will help us to generate for the graph. Okay, so now we plot it. We still do it one more time, and this time I will do the auto plot. Okay, I use the auto plot, and with the original data, I call the series name which could be the observed data. Okay. Of course, this will be very simple, right? All the observed data, this is real data, and they will be here. I add another layer. Okay, and now that will be the fit values, and the series name I want to put in, they could be called fit value. Okay, and if they are generated like that, they will go in this way. Okay, the data will be fit this line this way. You can see the very high correlated between the two data, between the observed data and the fitness values. But of course, this is the native method, so they make sense, right? All the data will be the same with the previous one, and we are mixing with the first observation because for the fitness value we don't have the data up to day 0 or something. So that's the reason why. Okay. Now let's just do it with the another layer. So I would do it fast. I would just copy it, and I want to just use for the X lab, Y lab, and everything else. So that's helped me to save more time. Okay, and let's do it. And you see that all the thing has been fitted here. Okay, That will be, you can see how the fitness values and the real observed data will be getting correlated with each other. And now let's go and check for the residual. So the fitness has been saved, right? The fitness has saved all the fitness values of the data, and we're going to check for the residual. Okay, so check the residual of the model. Okay. Alright, now let's just first of all say like we check for the residual. Okay, let's do it with like one more time, and I say it all here, name, right, of the when I already do it with the Google 200, and I fit it with the name model, and then I'm gonna check for the residual. Okay. So this will be all the residual, the difference between the real values and the fitness value. Okay, and that will be not end here. We will assign into the residual from kind of rest. Okay, so this will be anyway. I try to say that it's just an object, and this will help me to just generate for the graph of time series of the fitness value of the residual, sorry. Okay, and let's go and check it. So I one more time use the auto plot function. Okay, and I use for the rest, and then click on the X level. I would say date, but for the Y level I would say nothing. You know why? Because I with the fitness value we cannot say that this will be in USD or something. That's just the difference between the real value and the fitness value. So okay, so the residual don't have, we should not put in for the unit of them, even when we can do it, but it's not necessary. ZG title, I want to say like residual from the name method. Okay, let's do it, and we say like with the time series like this one, the residual is quite stable. They are totally random, right? They don't have the trend, they don't have the circle, and they also don't have the seasonality. So this look good for the residual. Residual should be anyway like a randomly plot, right? And let's just do it with, this is the time plot. Now we just go for the checks the histogram to see of the residue. Okay, so we can see how all the data of the residue kind of like fluctuate, and they are distributed. So GG histogram to be good here, and with the rest, okay, I generate for the GG histogram. What happened here? I make something wrong. Okay, GG histogram, and I'm going to do for, it's not just a histogram only. I put it into the title. Okay, this is title, and I would say this will be the histogram of the residue. Now this will be what we're gonna to do it for that. Okay, and lastly I'm going to check the auto correlation function chart of the residue. Okay, so with this one we already learned about the GG ICF, right? Remember about them. And let's check for the autocorrelation, how the current values are related into the previous value of the historical data. Okay, and let's do it with the GG title. This will be simple, and we say like ICF of the residue. Okay, that could be it. Okay, you can see over here everything has been like have not get beyond of the kind of like dust, blue line, so that means they're not of them are really kind of like significantly correlated with the current values, and they mean they don't have any kind of sign of the autocorrelation problem. Last of all, we use the check residual. Okay, check residual by to check all the property of the residual. Okay, by the Legend box test. Okay, so we can do it very fast, and in RStudio, and especially with the FBP2 function, we normally has been integrated with the check residual function, and they automatically generate for all the tests. And we do it with the what the people here, the native model, right? Native of the Google 200. And let's check it. It's like with this model, is there any kind of problem? And at the same time, they generate for all the graph, including for the time series. That's what I haven't done before. They are totally normal. We don't have the autocorrelation problem, and it looks like this one have not been normal distributed. And also, especially when you take a look into the Legend box test, p-values of the model, when they do it, they have the values of like 0.35551. That should be larger than 0.01 or 5%, and that means we don't the data for the residual, they are the white noise, and they don't have any kind of problem. They're good to go. Hello. So for the second part, we continue with the evaluating the forecasting accuracies. So with the previous one, we talk about the residual. That means when we generate for the data for the forecasting, we can apply them for the historical data and see like is there any difference between the observed data and their fitted values. But however, we talk about forecasting, right? We do all the thing about the futures, and we want to see like how accurate the model can be fit with the future values, how they are different to the real observe of the future values, and this be what. But however, actually we cannot get the kind of future value directly from today, right? We have to wait like if we wanted to do the forecasting for the data of the stock price in the next like 20 days, so we have to wait for 20 more days to wait until all the data has been released, and we try to just compare it and just validate it with the fitness value that we already generated for the forecasting. However, we have the better and kind of much more easier way. Kind of people will be smart, right? And they try to just overcome for all the kinds of problem. And this is how the people do. They just separate the data into the two different proportions. The first proportion they call the training data. So what the people call the in-sample data, and they use it to estimate for the forecasting method. And later they use another like normally 20% or 30% of the rest of the data in the futures. So they separate it with the kind of older data for the training data and the test data with the like 20 to 30%. To evaluate for the accuracies of the forecasting model. And if you already learned through some kinds of like artificial intelligence class or the like data mining class, you must really know about the test data and the training data. So I will now spend more time in this way of time, right? And in this section, to do it, when we try to just generate for the train and the testing data sets, so we have to use the function window or the subsets, so that way we can just separate the data into the two different parts, right? And the last thing I want to do in this one will be do for the how the people evaluate for the forecasting measure accuracies. So they use for the 4 or maybe 5 the different one of them, including for the mean absolute errors. You can take a look like what it gonna to do with that. The root mean square errors. Normally the people they spend most of the time to just do it with the 2. to compare between the model to see like which one would be the better. When you hear about the error, right, you mean you totally understand that. That means this could be the difference between the real values and the fictitious values for the test data. And the same, we have the percentage error including for the MAPE and the SMAP, but we most just focus on the 2-3 array. And the scale error, that means absolute scale errors for the MASE. So 4 of them will just work through all the course like a measure of the accuracy of model. So when we talk about this model better than the other, we talk about the accuracy rate, right? It doesn't mean that we use any kind of, I told you, simpler could be better. The most important thing would be the highly accuracy model. Not like a very complicated model. Sometimes the complicated model doesn't mean that can generate for very good forecasting. So we going to just compare between the different model with the which one have a smaller error, or that means all of this kind of number smaller. This will be the best model. Okay, the time series cross validation and the pi operation. Pi operation we already learned in some of the class already, so I will not spend time to talk about that, just in case that you want to take a look back. While the time cross validation, there should be something more advanced or content. So you guys will just have the test to just go home and just practice with the codes, but I will not spend too much time for this part. Okay. Now let's just go on to practice with the section. Okay, section 3.4 about the forecasting. Okay, accuracy measure. Okay, now let's do it. And so first of all, we do the subsetting. Okay, subsetting. So how we can do it? Like we use the function window. For example, if I say like AUS beer, one more time, remember Australia beer, right? If you want to take a look one more time about what exactly this would be quarterly Australia beer production, 1956 into 2010. Sorry. So okay, so I use the AUS beer to do for the window. If you already learned about window in the previous section, that should be very simple, right? So for the window, we have the start time, we have the kind of stop time. So put over here, I would just put it like with the star. Okay, but equal to in this time I would say 1995. Okay, and this will be the data start from the 1995 until the current data with the quarter 2 of the 2010, and you familiar with that, right? Okay, and now the time, another way for us to just do the subset would be try to use the same data, but in this time I use the subset function, and with the subset function they also can start at the end of the data, but I would just here with the star, so that equal to all the data. I just want to use all the data, but except not the last 20 quarter. I use the 20 quarter for like the 20 subsets. Okay, so for the quality like this one, so I would do it like the length equal to Australia beer. Okay, but then I mine it for the last 20, so I keep the 20 for the 20 data sets, and let's go to check it to see like is there any color problem. Okay, that's good. So we have all the data from we have all the data with the Australia beer, and we start like in the last 20 days, right? In the last 20, so all the data in the last 20 observation. Okay, so this be what I will gonna just say, like this will be for the training. Maybe I stop it with the like quarter 2, right? So with this will be for the training, and sometime I will say this for the testing data. Okay, test data, I can generate it like that. I can save it like that way. Okay, and do it the same. Okay, I do it all the time, and I can start do all the quarters the same thing. So I gonna to check it, and you see like if they are really the same with the Australia beer, but I gonna just use it for the tail function and x equal to 20. Okay, so you see both of them will be quite the same, right? Yeah, it looks like they are quite the same, except of course like this one I will just generate for, it's not just 20 but 21, because they count in for the land and minus for 2, so they also include for the like the quarter 2 of the 2005, but they should be fine. Okay, and that will be the way for us to do the subsessing. Now let's continue with the real example. Okay, and I want to check it by the model accuracies. Accuracies. Okay, and first of all, by the first day. Okay, I'm going to generate for the subset window. Okay, I'm going to do it with the first, I say it beer, and I generate like beer 2, I say the window function. Okay, I use for the Australia beer, of course, and I use the pipeline operation, the window function, and I want to start from like 1992. So when I put it here, they automatically understand that I start from the first quarter of 1992. If you want to clarify it like better, just do it like this way. Okay, the first quarter of 1992, and I would say C, and that should be 2007 at the fourth quarter. Okay, so I had the beer 2. We can also call it's not like beer 2, but we can say like the train beer, okay, or whatever you want. Okay, and another one I want to create for the test beer. Okay, and one more time with the same with the AUS beer function, but now do it and do the window. Okay, and I want to start now from like everything had been end from the quarter 4 of the 2007, so I want to start from the quarter 1 of 2008. Okay, that's everything. Okay, and I have a test data here. Alright, now this will be the time for us to the second stage. Fit the model into the data. So over here I want to use the naive function. Okay, I want to use the mean or the average method, and lastly I want to use the seasonal naive function. Okay, so let's gonna do it. So first of all, I say the beer fit number 1 model. They will be based on the beer train, the train data. Okay, the train beer data, and then I apply for the mean app function. Okay, I use with the like previous, like 10 x equal to 10, because remember, if you don't really understand why they do it, remember about the test beer. Okay, and we see like what exactly how many observations we have. We have a 10 last observation from the quarter 1 of the 2008 into the quarter 2 2010, so that will mean we have a 10 last observation. I want to just use the data to just measure for the mean forecasting of the next 10 periods, and I wanted to do it to do the validation compared to the test data. And the same thing happened again and again, but I'm just save the time and I use it the second fit model, and this time I will use it for the naive function. Okay, x10, And the last one, I want to use it not like fit 3, and this not but like as name. Okay, so I have 3 different kinds of function over here. If you don't want to use the name, you can see you also use the random what. Okay, random what function. Okay, in this case have time, and I want to just compare to another one that fit number 4, and this time I want to use the same beer, and I'm going to use a trip function. So random what forecasting x equal to 10 and a trip equal to true. Okay, let's just generate for the 4 function like that. And this would be now the time for us to just compare them by just block them and compare the kind of performance of the 4 different functions. So I use the auto plot function, and that should be what I already do. So for all the beer, in this way we're just going to just generate for all the data. So all the data from the 1992, right? I start from 1992. So a US beer, okay. Sorry. Yep. I success them and just have the window and start from like C 1992 Q1. Okay. Okay. And I'm going to use the autoplot function to just generate for the graph like this. They start it, and I'm going to just add in for the other layer of the thing. But first of all, that could be the auto layer. Okay, I want to put in another layer, and this time that should be the beer fit number 1. That should be the function. That should be the forecasting that I already generated by the mean function, the mean average method of the forecasting. Okay, so I say the series name now is could be the what the people call the mean method. Okay, look not so good. Okay, all right, and to do this, okay, I have to insert something. Pi equal to 4. I don't want to have the prediction interval. So the first layer have been added, the mean method, right? Very familiar. You already learned it in the previous section. I put another layer, but this time the automatically I do the same with the fit number 2, and this will be the naive method. Okay. Okay. The third time the same with the fit 3, but not the mean method now. That should be the seasonal naive. Okay. Okay, sorry. Yeah, I should not just put it like this way. Okay, that's my mistake. Okay, I generate this way. Okay, and we have 3 different methods already. And the last one, okay, layer, but now this will be at fit 4. The series now, this will be the trip method. Okay, so you can already see how the 4 different kinds of methods have been operated, and you see like the compare between the mean, the naive method, the naive with the trip methods, and the seasonal naive. That should be basically all the 3 of them, and of course like on way I can add in for the xlab. That should be for I put in the function, and I want to call it like year. Okay, this should be the just x level and also for the y level. this is what I call the megaliter. Okay, megaliter, and I want to have the title for the other function over here, and that could be the forecast for quarterly beer production of Australia. Okay, and if you really want to have some kind of color and have the name of the series legend, so I use the function guy. Okay, guy and the color equal to the guy legend. Okay, and I want to have the title equal to what I say forecast method. Now let's see it. This will be the graph, and this will be what we have already generated. You see, like all the things. Which one would be better? I'm not sure, 100% sure. So over here, one of the potential would be about the seasonal nave, right? Another one would be the drip. But however, all the things will be just like data visualization, and that's quite like subjective. So I had to base on something more objective, and this will be the time for us to use the kind of numerical measures. How can we do it? So we already have the data, right, for the graph, and we already have the kind also for the test data and the train data. So now is the time for us to just check for the accuracy. This one will be numerical measure. Okay, now let's go and check it. So we just use the one kind of function accuracies, and we check it with the difference between the Rapidminer model and compare with the test data. Okay, test beer. Okay, and you see like over here they already generate for everything, but the thing we really want to care about would be the MAE, the mean of the average errors, the root of the mean of the squares errors, something MPEs, MAP, and MASE. This will be all the five things that we really want to care about. So we compare that, just not with this model, but like three more times, right? The accuracies of the first model of the mean average. The second will be for the naive method. The third one will be for the seasonal naive, and the last one will be for the trip method, right? So all this is the time for us to just compare. We see like all over here, the model number 3, they have the smallest values of all the errors, like the RMSE, right? For the test data, you see like they just have like 14.31. They much smaller than the 62 something of the second model, 38 something of the first model, and 64 something of the fourth model. And the same thing happened with the MAE. MAE will be very small compared to the other. The MAP of them will be very small. They're just less than 1, while the other will be about 14. And the same thing happened with the MASE, just like about 0.1, while the other like about 2.44 and then 4.1. Okay, so according to what we already see, this one you can say like when comparing the accuracy measure to seasonal naive method do bad does best. Okay. Right. The other part, like advanced part of the time series validation, you will have to do it by yourself. Okay. Hold on, right. The section 3.5 talking about the prediction interval. So if you already learned about the interval estimates in the probability and statistic or other kinds of statistical tool, statistical related course, you already must know about what exactly they will be the interval, right? They will be the kind of like a drop and the interval of all the values that generate and just fluctuates around for the mean values. And you also have to be must be very familiar with the kind of like confidence level of the 90%, 95%, and 99%. So technically, people will, when talk about the interval, they would just defaultly talk when they see the confidence level of the 95%, and they generate for the prediction interval by taking for the mean value plus for the critical values of 95%. This will be a natural. This will be a the normal distribution. So they will use the this will be critical values of the 95% confidence level and generate it, and time for the standard deviation. So basically they will be all the method they do for that. But however, we can generate it easily by in the section by practice 3.5. So prediction interval can be easily just generated by the function of the autoplot. So when we don't really clarify about the PI, so they just generate it easily. Okay. So for example, when I talk about this one and I say like the Google 200 one more time, and I use the nav, okay, function, okay. So I do the prediction for all the nav, and this generate for all the graph that you can easily find that they have the point forecasting, they have the low 80% and high 80%. That means with the interval confidence level of 80%, and they generate for prediction interval like that from this into this, with the 95% confidence level from this into this, and the lower and the higher, like the bigger like in the further observation, in the further prediction with the further periods, we expand, and all the graph is going to do like that. We can check it, right? We can check it by the auto plot function, okay. And if I just say like x equal to maybe generate normally with this one, okay. So they normally just generate everything by this way, okay. But however, when I really clarify about the level, okay, so the level they equal to just 80%. When I generate it, they will just generate for the 80% prediction interval, okay. If I change it like 95, okay, so they know that they will going to just generate it for this one. You can at the same time level, you can put in like a lot of different number, like it's just not stop with the 90%, 80 and 95%. Of course they generate for the two of them at the same time. If I'm gonna do it like with the 90 and 95, you get the same with the different 3 layer, okay. If you really care about that, this will be 80%, 90%, 95%, and the largest, but with the lightest 6, that's going to be the 95%. That's what we're going to talk about, okay. And easily we can all the time generate for all the graph like that way. With the same way we can do it, but the time now I'm going to just generate it for the bootstrap, okay. With the bootstrap really help in some way when the data is not really so clarified, and we don't have a lot of data. This takes for a while, but however they generate for the graph, and everything will look more kind of like reasonable, and they closer to the section, okay. They automatically generate for the 80% and 95% of the level of confidence, and this will be harder to generate. Okay, last but not least, this will be the last section about the introduction of the forecast package on R. another tool, of course. So the forecast package is loaded automatically when we load for the FEV2 package. You already know about that, right? And they include for the different kinds of methods. Like actually they include for the mean method, right? The naive and the seasonal naive method. The random walk for forecasting, record storm, and for the sex, the horn. That will be for all the kind of exponential smoothing, the spotlight, and the forecast. So this all the thing we're going to do it on this function. Another one we can later in the first chapters, first homework, I will just introduce you about how to use it for the Rapidminer. So Rapidminer, that will be the interface and how to include for like 20 different operator for time series forecasting. So you don't have to really worry about what types of we're going to do with that like that. And Excel too. If you really go on there and the formula function, actually they have the forecasting method also. At least like about 5 the function will be available on your current Excel version from 2016 or above. They will be available over there. Okay, so we go on the practices and just do it with the forecasting packet right here. Okay, forecasting packet. And right over here, remember when we use the function forecast, they will just like automatically use the ETS. That's E. The S will be E will be errors, T will be trend, and this X will be season. Okay, seasonality. Okay. They will automatically generate for the forecasting method, the same with the naive, the same with the like as naive, or the same with the kind of like average math or the mean function. However, we're gonna just use this for our kind of part. So the same one more time, I use the Google, okay, and I use Google 200, and this time I just use the forecast function, and just like that, or maybe I will put a little bit more, like I will forecast for the next 4. Okay, and you see like they automatically generate everything by the forecast function like this way. Okay, and you can also put in for the auto plot to see how everything will be plotted into. Of course, you can go and this with ETS if you just defaultly put in. We will talk about that in the later chapter, but normally right now you can easily just generate it by the forecast function like that way. And the same thing we can use this with the AUSB or something. Alright, if you want to try it, and I'm check it with the forecast. X equal to 4 in the 4 hash periods, and I use the auto plot function to generate for the graph. You can see over here they also generate for that automatically. Very convenient. Okay, and I think that should be enough for the today's section. We already go through some very complicated part of this section, including for the residual diagnosis, the forecasting accuracy measures. Also, I introduced about prediction interval and how you use for the forecast function in the forecast package in R. There was some further video about the Rapidminer and Excel if we are possible to see it later. Thank you a lot.